Hello, everyone. Good afternoon, good morning, good whatever it is. We wish you a very warm welcome to the CAE Department Seminar Series. I'm really pleased to have with us today our speaker, who is our department chair and professor in civil and architectural engineering, Professor Xianming Shi. He will talk about engineering biochar for carbon negative concrete and beyond. Dr. Shi is, as I mentioned, chair and professor at CAE at the University of Miami. He is the founding director of the National Center for Transportation Infrastructure Durability and Life Extension. He is also the editor-in-chief for the Journal of Infrastructure Preservation and Resilience. He is an ASCE fellow and he is also senior member of the National Academy of Inventors. He has more than 20 years of experience in R&D. In 2024, he founded Carbon Sylvanus Company. Two of his projects won the ASHTO Sweet 16 Award and Supplementary Award, respectively. We will not discuss his other awards and achievements because I don't want to talk for 15 minutes. He obtained his PhD in chemistry from the Chinese Academy of Sciences in 1999. So thank you very much, Dr. Shi, for doing this, and the floor is all yours.
Thank you so much, Dr. Pranoy Sornani, and welcome everyone. So today I'd like to share with you a few things we did with this magical material I am really fell in love with. uh, so engineering biochar for carbon negative concrete and beyond is my talk. Before I start, a little bit infomercial in terms of who we are for those of you who don't know about University of Miami. So, because I know this is going to be on the YouTube. So, yeah, we are in a wonderful city, Coral Gables, which is very close to Miami, and there's a lot of entrepreneurship in the area and abundance of opportunities and good food. So, with that, what's the background of this? Before we jump into the tools or solutions, truly, human society, face tremendous challenges when it comes to the built environment, especially. For example, the transportation system, as we know it, is getting really old and aged, and there's a lot of deferred maintenance, and the durability and reliability of the built environment is compromised by many, many different distresses. On top of that, we also have the climate change as we know it. It's not just the CO2, but also other greenhouse gas emissions. So when it comes to the specifics, the man-made CO2 or CO2 equivalent emissions, as you can see, both building sector and construction materials do contribute a significant chunk, and one of which we know is the use of cement. Ordinary Portland cement, typically 1 ton of cement, takes about 0.8 tons of CO2 emission. So that's a challenge we need to tackle. So what is our vision? The vision is really making infrastructure part of the climate solution, because we always consider infrastructure as part of the problem when it comes to climate change. But here's a pattern we applied back in 2023, I believe, and the IP is already licensed to a company in the UK. Basically, the way we do it is leverage this material known as biochar. Biochar is nothing new. The farmers in Africa had played with this material for thousands of years when it comes to soil amendment. But in recent decades, because of the interest in the biochar sequestering CO2 and slow down the release of CO2 back into the atmosphere, the agriculture industry has been increasingly interested in biochar. But when it comes to the construction industry, this is relatively new. So we filed this patent back in 2023 and licensed last year. And our IP is more focused on how to make this biochar more valuable. As I'll share with you later, we did some surface engineering of this biochar, and we launched the company in 2024. And this chart on the bottom right shows the x-axis is the particle size, the y-axis is the specific surface area. The typical coarse aggregate or rock we use, or gravel we call it, in the concrete is relatively large. You can see at the bottom right, and if you can find a way to make it really, really small, we're talking about nanometer size, for instance, 1 nanometer, for reference, human hair is about 80 microns or 80,000 nanometers in diameter. So if you can make things really, really fine, then you will achieve, between 10,000 to 1 million square meter per kilogram sort of surface area. And with that, there's a certain nano effect, and the material becomes much more reactive. So that's kind of the guiding principle for the IP we produce, is to precipitate nano or submicron sized calcium carbonate on the surface of the biochar, so that, because biochar is mostly a carbon-rich material. I mean, depending on the feedstock and the pyrolysis procedure, you could have probably 40 to 95% carbon. So in a way, it's counterintuitive. Why do we put carbon into concrete? Because traditional wisdom will tell us that's silly and it's not even allowed, because they may take away a lot of the admixtures or chemical additives in fresh concrete. In many states, for instance, the Department of Transportation would not allow anything having a so-called loss on ignition higher than 3%. In other words, here we're putting in a material which has a lot of carbon, or a high loss on ignition, then that's counterintuitive. That's exactly where, when you challenge traditional wisdom, innovation occurs. So again, in addition to putting engineered biochar into cementitious composites such as concrete, mortar, grout, or paste, we also try to engineer so that it's suitable for asphalt. As you can see here, for asphalt pavement, when we pave it, there's a lot of toxic fume coming out of the pavement. That's one issue. And also, asphalt pavement by itself has its own carbon footprint. So we have an ongoing study, even though it's not part of today's talk, is we have an ongoing study sponsored by U.S. Department of Agriculture, trying to divert agriculture waste or farm waste towards this process to produce biochar, and then biochar would replace a part of the asphalt binder and some of the mineral fillers in the asphalt mixture and make it net zero. So today, in terms of the beneficial use of biochar in concrete or cementitious composites, I share with you 4 different studies. Actually, some of this is not yet in the published domain. The first one is sponsored by Washington Research Foundation, and my team is here when I was a professor at Washington State University a couple of years ago. So Ayumi, Japan are the main doers for this project, and you can see we look into 2 types of feedstocks, wheat straw and a biosolid. I believe it's a cow manure, and then through a process known as pyrolysis, you basically heat it up to really high temperature, typically 500 to 800 degrees Celsius, with very little oxygen, then you generate biochar. And again, the background is that we use a lot of concrete as in industry progresses, we use about 2 billion tons of concrete, and it's estimated to double by 2050. And concrete industry contributes to global greenhouse gas emissions, roughly 6 to 8%. And biochar is a carbon negative material. So basically imagine the photosynthesis of plant species, very efficiently grabbing CO2 from the air and store it as a solid carbon. Now, if we find a way to use it as, say, a greener cement, then at the end of life of the concrete, it will never go back to the atmosphere. So that's a very efficient way of storing carbon or sequestering carbon. Of course, alternatively, what naturally happens is the biomass would either catch fire or go through fermentation and release the CO2 or soot or methane. Those things are very powerful. Actually, methane and soot are more powerful than CO2 when it comes to global warming potential. The challenge, though, is traditional wisdom, again, because of that loss of ignition or incompatibility with concrete admixtures. Typically, people are playing with 1 to 3% by weight of cement when it comes to exploring the use of biochar in concrete. And that was kind of an unwritten, unstated assumption. And then in 2023-ish, we decided to challenge that conventional wisdom. So this project aimed to explore different ways to modify biochar to improve its quality or compatibility with the concrete. So we published a sort of proof of concept paper in March 2023. And then here's a study where we first start from this cow manure derived biochar. And as you can see, we used a concrete washout water, which is another waste stream from concrete production. And it has relatively high pH around, say, 12.0. And you can see we dry it, then we grind it, we sieve it. And the purpose of using the washout water is because it has not just the high pH, but also calcium cations in it. And CO2 from air would react with this calcium cations and precipitate the nano or submicron size carbonate or calcium carbonate on the surface, as shown here under the scanning electron microscope. So we explored several mix designs. Each column is a different mix design. Of course, for those of you who are less familiar with the pound per cubic yard, 1 pound per cubic yard is about 0.6 kilogram per cubic meter. And we used the water cement ratio 0.4 for these concrete mixtures, and the sand to cement ratio 2.0, the gravel to sand ratio 1.75. And we pre-soak these biochar, as I showed earlier, some of, before grinding is coarse biochar and after grinding is fine biochar, less than 150 microns, well, which happens to be about twice the size of human hair. So we use these symbols, fine biochar is BC, coarse biochar BS. Also, in one of the mix designs, we also explore adding 10% of silica fume, yet another industrial byproduct to replace cement. So we got 1, 2, 3, 4, 5, 6 mix designs. We want to test them. First, the good news is that biochar amended concrete can achieve better strength at 28 days than the control. You can see here 100% cement concrete is around 6,000, 400-ish PSI. And then you look at 5% replacement of cement using the fine biochar, then you're achieving some improvement of the compressed strength. Similarly, this one is 5% of cement being replaced by fine biochar and 10% of the sand being replaced by coarser biochar. And again, we're seeing benefits in some of the mixed designs. That's very encouraging. Keep in mind, our intention is not to truly improve the strength. We just want to achieve at least comparable strength. The point is to reduce the carbon footprint of these mixed designs. And continuing that, again, we went a little higher, 10%, still very good. And even 10% replacement of cement and 10% replacement of sand, they're very good. And now the different color actually shows the 0T basically means we didn't go through any sort of wet dry cycling, and 1T is one cycle wet dry to see the different levels of carbonate precipitation. So what about 7-day strength? Actually, in some cases, even better. You can see in this scenario, we're achieving 32.6% better strength than the control. So not only we are reducing the carbon footprint of the concrete, but also we're achieving higher strength at 7 days. So that's really good news. Now the question becomes, can we sequester more carbon or CO2 in concrete without losing the strength? So we played a few different mix designs, as you can see here. I highlight the ones which are very promising. So roughly speaking, you can replace cement at 10% with this specific product. As I'll mention later, unfortunately or fortunately, I don't know, not all biochar products are the same. They are very different depending on the feedstock, the pyrolysis parameters. The devil is in the details. Now, if we want to achieve carbon neutral concrete, here's a very interesting mix design. Of course, we had to rely on 10% silica fume to replace, the cement binder, and then we used 10% of the engineered biochar to replace cement, and then 10% of coarse biochar to replace sand. And you can see, compared with the control, we're achieving roughly 28 to 30% better strength, both at 7-day and 28 days. So, moving on to some other thoughts in the same pattern we found is, what if we chemically treat the commercially available biochar? Can we do some magic with it? So we play with two types of biochar, one derived from cow manure, one from wheat straw. And we use different chemical agents. We know we're trying to induce some sort of surface functional groups such as hydroxyls or carboxyls on the carbon surface. So the good news is, in some cases, yes, we are able to achieve improvement in compressor strength at 28 days. And the most effective one seems to be the one using 10% sodium hydroxide treating the biochar for 10 hours. So, and we also did the Fourier transformation, or FTIR, Fourier transformation infrared spectroscopy, and basically shows, yeah, our hypothesis was true, that we did induce the formation of hydroxyls and carboxyls or even ethyl groups on the surface of the biochar. That's why they worked better, and they, chemically reacted with the cement hydration products, basically. And now moving on to another possible application scenario or use case scenario is, we want to see whether or not we can achieve even more biochar into another specialty concrete, which is cellular concrete. In that case, you're not aiming for really high strength. Typically 5 megapascal or even less than that is good, good enough. And you are really trying to achieve sound insulation, thermal insulation, or things of that nature. So here we aim for 30% replacement of cement by biochar. And we had a few mixed designs. The AOS is basically a foaming agent working in combination with sodium phosphate. They seem to foam and stabilize the foam inside the cellular concrete. So as you can see here, when you're foaming it up and add so much biochar, 30%, of course, you're gonna lose some of the strength, but they're still not way better, but they're still sufficient to serve as cellular concrete, because usually these are not used as structural concrete. They're used as separators or sound insulation, thermal insulation, and fire resistance, because these properties are built in because of the built-in porosity of the pores you saw in the biochar. So you look at the thermal conductivity, they're actually well within a range designed or specified for these type of cellular concrete. Well, that's the first study. So we show that biochar has great potential, and despite a conventional wisdom of not putting carbon-rich material into concrete, we did it anyway, and it works out. And the key, though, is we need to understand, what type of biochar and what type of microstructure or surface chemistry. Now, the second study, again, stemmed from the fact that, as I mentioned earlier, most DOTs or state departments of transportation would not allow you to put in even a fly ash that had too much carbon in it or a high loss of ignition. The reason is that, again, the conventional wisdom says the carbon or the free carbon in the ash, in this case, in the biochar, would consume the air entraining agent and make the freeze-thaw resistance of the concrete really poor. So, and the counter argument in this case is, okay, what if we don't need the air entraining agent, because we have built-in porosity at the micro scale, as you saw under the microscope, then maybe we can engineer in such a way that we don't depend on entraining admixtures to give the concrete its freeze-thaw durability. So the short answer is yes, we were able to achieve that goal without use of an training agent. So the x-axis shows a number of these mixed designs. The C stands for the group with just concrete without any entrainment, and that strength is slightly reduced when you introduce an entrainment. That's a well-known fact because you introduce a little bit of defect, tiny little micro-sized bubbles. And interestingly, with 5% replacement cement by biochar and 10% replacement of sand, we actually achieved significantly higher compressive strength at 28 days compared with the N-trained concrete. That's a good starting point. Now, we also demonstrate at 5% replacement level, the use of biochar actually significantly improved the fracture behavior of the concrete. Again, fracture behavior is pretty important in many of the use case scenarios, so that's really good news. Now, we also found that the use of this biochar to replace 5% of cement reduced shrinkage of concrete. Again, yet another win, because shrinkage-induced cracking is a concern for the durability of concrete in many cases. Now, here's another one. If we further not just add 5%, replace 5% of cement, but also replace another 10% of sand, and the shrinkage further reduces. So again, it's all good news to this point, right? Here's the bad news. So when we incorporate biochar, we do see an increase in water absorptivity. This x-axis, the first one, is between 0 to 150, but remember this is a square root of the time. So basically this is indication of the micropores, the capillary action taking water from the adjacent environment. And the secondary absorption also increased, which is typically water coming from the environment into the concrete and filling the larger pores. So this is a concern, but there are tools such as admixtures that can help reduce this water absorption. So now, but we haven't done any real testing to mitigate that. We just want to see, okay, there's some benefits we showed earlier, and here's a downside. But if we balance all of that and we subject the concrete to rapid freeze-thaw testing, after even 150 cycles, you can see the air-entrained concrete versus this 5% cement replacement, 10% sand replacement, we're achieving comparable or actually better strength or residual strength because the initial strength was high, so your residual strength is still higher than the control. And when we calculate the durability factor is almost 73%, which matches with air-entrained concrete. So it's all very good. In other words, we don't actually need an entrainment for biochar amended concrete to be used in freeze-thaw environments. So switching gears to a third study where it's sponsored by Washington State Department of Commerce and two university translation centers I used to lead or co-lead. So here we explore 4 types of biochar products. They're all commercially available. Again, there are hundreds of companies in the US who manufacture biochar using locally or regionally available feedstocks. However, their intended market usually is the farming industry, right? Like soil amendment. So we are trying to leverage these commercially available products for a different application. As you can see, from the feedstock could be woody biomass, such as softwood wood chips. I believe it's from Oregon. That's why we named it OR. And another one is with straw derived biochar from Washington State, and this one's from cow manure, and yet another one is from wastewater treatment residual. And this specific product, unfortunately, turned out to be very poorly produced. The quality was not sufficient for it to be used in concrete. So with a little bit of trial and error, we decided to use the ground biochar as replacement cement for the first two types. And for the third type, from biosolids, we let it go through the CO2 weathering process, as I discussed earlier, with concrete washout water and sometimes wet dry cycling, and then replace a part of the sand. Again, the key message is not all biochars are the same. They behave quite differently from each other. So it's not like your traditional, well-produced, say, ordinary Portland cement. So it's not a plug-and-play technology at this moment. So again, the same usual, with grinding, we'll get to ground biochar to replace 5, 10, 15, 20% of cement in the concrete. Well, actually, in this case, we start from cement paste. So just for those who are curious, what's in the concrete washout water? Again, pH 12.0, and there are all kinds of trace elements. There's some calcium, some potassium, some sodium in it, which is what we need to enable that precipitation of carbonate on the surface of biochar. And for this softwood chips derived biochar from Oregon, you can see we basically, I know it's a very busy slide, but we basically tried different dosages, 5, 10, 15, 20%. And the different color bars shows 7-day strength versus 28-day strength. And then we also try to see grinding it for different duration. In other words, achieving different size gradation and see how that behave. I mean, how would that affect the compressed strength of the cement paste incorporating such biochar products? So in a nutshell, we see higher strength when we grind 50 to 60 seconds for this Oregon biochar, and for the next one, it's about 60, and in some cases 30 seconds, which is a little surprise. But again, when you add so much, 20% replacement cement, you do see significant reduction compared with the control in terms of strength, even though they're still well above 5,000 psi. Now, here's another one, again, 50 or 60 seconds. And what does this mean? We'll see grinding to different amount of time. I mean, basically it's getting typically finer and finer and until it approaches the size of ordinary Portland cement particles. So the assumption or the observation is that when you grind it to such a degree, it's very similar in terms of size gradation to the ordinary Portland cement. They induce better products in the end. Now, for this wheat straw derived biochar, it's not as a beautiful correlation, but it's close enough. So again, for the ones replacing the sand, we need to make the biochar a little stronger or stiffer. So the carbonation or the precipitation of submicron or nano-sized carbonate will be essential. So we did that and trying to replace sand at 10% or 20%. And we also tried different number of cycles of CO2 weathering. The thing is, with those biochar products derived from woody biomass, they're not really good sand. Even after carbonation, they're very problematic. So we don't want to use them in these actually mortar samples now. However, for the biosolids derived biochar, we were able to get to a reasonable balance. When I say balance, I mean achieving reasonable compressed strength of the mortar samples, and at the same time, getting some carbon credit, basically sequester as much CO2 equivalent as possible. So we were achieving a reasonable balance. Again, we did try to optimize the number of cycles we have to subject the biochar products to in order to get to the right amount or right size of carbonate. That's a lot of trial and error. Again, we did the TGA or thermogravimetric analysis, which shows that there is a peak between 500 and 600 degrees. As we subject biochar to more cycles, that peak sort of disappeared. However, here's another peak, which is corresponding to calcite. It increases over time. So when we plot it, we see the x-axis, the number of CO2 weathering cycles. The y-axis on the left is the amount of CO2 weathered products. The black line is almost a linear increase over the number of cycles. However, if we only focus on the calcite as part of the product, it sort of peaked around 10 cycles, which is the red line. So with that knowledge, now we move on to different mix designs. Now in this case, we started from paste and then mortar, and now we're into concrete. So to accelerate the test, we cure them under 40 degrees Celsius, so sort of double the rate of hydration. And you can see the good news is that we're achieving about 25% better compressor strength at 28 days when we replace cement at 5%, either with the Oregon softwood chip derived biochar or the Washington State wheat straw derived biochar. Now, but that strength is almost too high. We don't necessarily need that kind of strength at this moment. So what if we add even more biochar? Then we achieve in this group, again, replacing 20% of sand with the weathered biosolids derived biochar, then we still achieve comparable, slightly lower strength, but that's typically efficient, especially for pavement applications. But then we may be able to incorporate a lot more CO2, gain a lot more carbon credit, and also divert more waste streams towards beneficial use. So dry and shrink-wise, it's different than what we saw in the other study. We are seeing slightly increased shrinkage because, well, every product is different, I guess. What's interesting here is my collaborator, Dr. James Amnett, did some preliminary environmental life cycle assessment, or LCA, to see how much carbon credit we're getting. So if we're replacing cement at 5% with this biochar, say Oregon versus Washington one, we're achieving quite different numbers. So in other words, how to read this is, if we're using the one from softwood chips from Oregon, 5% were reducing the CO2 carbon footprint. The carbon footprint of concrete by almost 47%. In other words, if we are able to replace cement at 10%, we're getting really close to carbon neutral or net zero. However, with wheat straw, we need a lot more. Again, the devil's in the details, depending on the energy consumption, the byproducts like the particulate matters, whether or not you recycle the waste heat. Yeah, there's a lot of detail into these calculations. And also for the biosolids derived biochar, actually, we're not getting much carbon credit. It's like 5%, right? Like, even if you replace sand with 20% of this biochar, you're really not getting much of that carbon credit. However, an unintended benefit for diverting biosolids into concrete is that this research already demonstrating that you destroy the PFAS, which is the forever chemical, and that's a major pollutant or emerging pollutant. So the benefit is not so much in the carbon credit, it's more in waste management or pollution avoidance. So again, not all biochar products are the same, and there's certainly more room for innovation or more room for optimization, because these products were not created for the construction industry per se. Now, water absorption, again, actually, in this case, the initial rate, as you can see here, is not too bad. It's basically comparable with the control, in some cases even slightly lower. But the secondary rate is in some cases, especially when you incorporate too much sand replacement by biochar, it does increase. So again, there are tools to reduce this kind of water absorption if needed. Just to share with you a picture of nanocarbonate. Since we talk about nanocarbonate, here's the direct evidence. You actually see them, right? right-hand side, the SEM or scanning electron microscope image shows the raw biochar pretty smooth, but after carbonation, you see the nanocarbonate. But the challenge is that in the field, we probably don't have this kind of ability to control it. So we did something really rough, as you can see here. It's a very simple 2 cycles of wet dry under ambient temperature with the concrete washout water. That's how we did it. And then we demonstrate, we deployed about 145 feet long sidewalks with various mix designs, the 5%, 10%, whatnot. Each mix side by side with some control mix designs, we embed sensors to measure strain, temperature, moisture every 20 seconds. So we've got more than 18 months of data so far. We need to analyze the data and potentially publish it in next year. The main observation so far was, yes, we're seeing a little bit more strain. Cumulative strain in the biochar amended concrete, even though it's not to the concern level. Mostly because, again, the moisture, the water absorptivity we were talking about earlier. So in other words, if we are concerned about that, we should incorporate some waterproofing admixture. Yet another one study is using biochar to replace 30% of cement in the specialty concrete known as ECC, or engineered cementitious composites, also known as strain hardening cementitious composites, or SHCC. So this study published in Cement and Concrete Composites last year. And we basically, again, look at the issue. Nobody has ever done this before, of course. People were thinking about, 3% or less, but we're thinking, can we get to 30%? So the short answer is yes. You can see here 3-day strength, compressive strength. You do see significant difference, reduction at 30%, but over time, once you get to 28 days, you're actually not seeing reduction. You're actually seeing slightly improvement of compressive strength. Similarly, in tensile strength, you're seeing a little bit of reduction, but that's okay. The tensile strength, at least at 20%, you're seeing much better. Even 30%, you're seeing better tensile strength. Let's see. Okay, the first cracking strength sort of peaked at 10%, but even at 30%, you're still comparable with the control. The strain capacity did decrease compared with the control, but again, even that, is still above 5%. Sorry, not really. Above 2.5%. So that's sufficient in most applications. So fracture toughness again peaked around 10% replacement of cement by biochar, but even at 30%, they're very similar or slightly better than the reference. So it's all good news. And what about drying shrinkage? Okay, here we also see 24% lower drying shrinkage. That's good. Water absorptivity, again, that's the bad news. 48% increase. So unless we use some sort of admixture to mitigate that, or depending on the service environment, whether it's concerned or not. So gas permeability, again, is an indicator of physical microstructure, how dense they are. Here we're seeing 22% increase, which means they're not as dense as a reference. Again, that could be a concern. So to conclude, biochar ECC can achieve high strength, 90 to 100 megapascal. And we can reduce strength and improve the interfacial transition zone up to 10% replacement of cement. And the environmental life cycle assessment shows up to 78% CO2 equivalent reduction. And the overall balance is that if you only replace 10 to 20% of biochar, you probably achieve a good trade-off. So with that, I conclude my talk. And here's the, summary, shows the type of work we do as a research group at different life cycle stage, whether it's mixed design or towards the end, corrosion protection. Our focus is really trying to improve the durability of the concrete and also divert waste streams towards beneficial use. Let's see. I'll quickly go through a few additional recent studies. They're not related to biochar, but they could be. For instance, like this one, we have another pattern, which is pre-treatment of sand and gravel, and then you can achieve significantly better strength and durability with a very simple treatment. Yet another one is self-healing UHPC or ultra-high performance concrete. We produce these microcapsules, and we demonstrate you can enable much better self-healing in UHPC. And again, the next step, we're basically, instead of using microcapsules, we're using biochar as the carrier of the healants. We have another patent just filed last week, basically demonstrating we can use biochar as a carrier for healants. In that case, the healants are no longer these chemicals. They are a mixture of two different types of bacteria. Now, okay, yet another one is the, again, ECC or strain hardening cementitious composites. We demonstrate that we can use very cheap recycled masks or recycled clothes to endow the ECC with much better fire resistance. Basically, without it, the ECC would have this explosive spalling, but with it, they are basically sort of intact under fire attack. So with that, I would say the future, we still have a lot of work to do. We would love to continue diverting waste streams towards beneficial use based on our domain knowledge and based on creative thinking. And because of the aging infrastructure, because of the emerging technologies such as artificial intelligence, digital twin, drones, robotics, and so on, there's a lot more civil engineers can do, and it's pretty exciting times, in my opinion. Thank you. That's all. I'll work on your questions.